Okay, so here is the second of the 1.1 sections, 1.1.2, and that is going to be types of processor. So we're going to cover the whole of 1.1.2 in this video, so let's get on with it. So when you design a processor, you have to write out a list of the commands that the processor is going to have. So like 0 is going to be add, 1 is going to be take away or whatever, subtract. And so this is called the instruction set. And basically, you can sometimes download these for certain processors, and it will tell you exactly what each machine code instruction does. And so so that's basically what an instruction set is. So there are two types of processor instruction set that we need to look at. One is called CISC, which is the complex instruction set, and one is RISC, which is the reduced instruction set. Computer, by the way, that's what the C is, reduced instruction set computer, but I didn't bother putting that on. So CISC. So CISC essentially has a large instruction set. So there's lots and lots and lots of instructions which are very specific. So think of it as as we go along, I'll explain it a bit better, but think of it as it has very complex instructions. So, like in human speak, it might be like fetch something. So you go and fetch something. That's quite a complex task. You're not saying stand up, walk towards, put hand down, pick up object, bring to me. You're just going to fetch that. So you've taught it to do a more complex thing. So a single instruction can do quite a few things in it, which means that the program can be shorter, because obviously if the instructions are more complex, you don't need to break them down as much. They might do what you want with just one line. Okay. So obviously we have the opposite of that, which is the reduced instruction set, which is basically a smaller number of possible instructions, but they're quite simple and they can be built up to do the same thing. Now, the benefit of RISC is that they only take a single clock cycle. With CISC, all the instructions might take a different number of cycles, 4, 8, 2, 3, 1. But with RISC, they all take a single clock cycle, so a single fetch decode execute to perform in one clock cycle. So let's look at them side by side as code. You see, these are, I made these up a little bit, they're supposed to be memory addresses, but they're very similar to what a real instruction might look like. So multiplying the numbers found in these two addresses, and we're going to store it in this address. So this is a single instruction in CISC because they've hard designed all of this, actually in the CPU in one instruction. So that could be 58. In RISC, you would have to write load A, that's load to register A. So loading what's in memory address 7 to register A, what's in memory address 8 to register B, get the product, which obviously multiply, and then store the result of what was in register A in memory address 7. Now this is doing exactly the same thing. Okay, it's multiplying what we find in there, and storing it in there. But you can see the difference. Now you might think this is better, CISC is better. But there are issues, because the reality is, what if you haven't got the instruction that you need? Well, then you've got to build it up, whereas RISC, you've kind of got the flexibility of any instruction. They all take one clock cycle. So let's have a look at the robot that I sort of invented that doesn't really exist. We'll call it Z robot. Imagine we have a robot. Okay, this could be a sort of other thing. So like in CISC, we teach it two commands, those two commands, but in RISC, we actually have to give them the commands manually like this. But this obviously gives us more flexibility. Okay, and here is the comparison. So CISC is quicker to write programs in, but I put a caveat in that only if you're writing in low level, because obviously if you're writing in Python or whatever, how it gets compiled is not relevant to you. So not necessarily true. If you're writing actually in machine code or assembly, really, then it makes a difference because you're only writing these instructions. But if you're writing in a high level language, then, at the end of the day, you don't have to worry about the final result. The compiler will have to do that. The programs are smaller in memory because, look, obviously, programs smaller. When you load the program into RAM, it's only going to take that much. That's going to take 4 times as much. And it's easier to make a high-level compiler as it has less to translate, because obviously, it's got less complicated things to do, because obviously the instructions are just like one instruction, rather as obviously when you make a compiler for a high-level language, if you want to multiply two numbers and you've got a CISC computer, all the compiler's got to do is make that command. Whereas obviously it's got to do these 4 commands with RISC. So the compiler is more difficult to make because it has to do more things. However, RISC is simpler to design as the circuits have less complicated instructions to perform. So if you have to design the circuit to do all of that in one go, that can be quite annoying. Whereas here you kind of got decomposition. So, you know, you've only got to make that instruction's got to do one thing. So it's a little bit easier to design the circuits for. And because there's one, this is an important one, because they're all one clock cycle for each instruction, this helps to enable pipelining. Because if you think of pipeline, remember, as one is fetching, another one's decoding, another one's executing. If the executions take different numbers of cycles, that's not going to help pipelining, because you can't then be moving on to the next step at the same time. Whereas if they all take one clock cycle, then it's a very nice conveyor belt style thing of going in, getting fetched, getting decoded, getting executed, one cycle. Yes, programs are smaller in CISC, but memory's so cheap now, space is not such a problem. And often in programs, it's not the program that takes a lot of the memory anymore. It's the data, which is, so, you know, like for example the video you're editing or the game graphics, and that's not going to change. And because programmers can build the programs using smaller, simpler instructions, they often, not always, often run faster. What I mean by that is, let's say I wanted to do these 3 parts, but not do this, and do something else after that. I might have to still do all of that and then do the thing after, even though I don't really want to do the store 7. Maybe I'll do something here as well, like add 2 to it. Now I've got to do that, which is then doing an extra instruction, and then do my add to it or whatever. So you can see that it's possible that it could be simpler, and therefore more efficient and faster. Right, so let's go on to the next part. So that we just covered there was this part here. So now we're going to look at GPUs and their uses, including those not related to graphics. So let's go down. So a GPU is a type of coprocessor. And what a coprocessor is, it's a processor which basically helps out the CPU. They generally have a specific job, because otherwise why would you want one? So because the CPU is a general purpose processor, and then it's used to do many things, there are obviously some things that a coprocessor will be better at. So one of them is digital signal processing, is another coprocessor. We're not talking just about the GPU here, these are other ones, right? So the GPU obviously is very good at the graphics, because it stands for graphics processing unit. So obviously a GPU is very good at 3D graphics. But other coprocessors you could get, you can buy video editing encoding cards, which you plug into your computer, and they're very good at encoding videos. Some streamers use them. Although I think computers nowadays are so fast, I don't know if you need that. So there are other types of coprocessors, ones that are good at a certain type of maths. I mean, science could use that, and the very others. But we're going to look at the GPU. So GPU is a 3D graphics coprocessor. It's very good at the maths surrounding 3D graphics. So inside a GPU, there are thousands of cores in it. The cores on a GPU made by NVIDIA are usually referred to as CUDA cores, and on AMD they're called stream processors. But basically they're just cores. Okay, my GPU currently has 8,704, but this might be dated. It's in 2022. So you can see they have a lot of cores, right? 8,700 cores, much more than like say a 12-core CPU or something like that. So that's a sort of a visual example if you can't get that, but even that is limited. How many have we got? 2, 4, 6, 8, 10, 11. That's 22. So that's obviously nowhere near the actual number. That's only got like 500 squares in it, and obviously 8,000 is the sort of modern. So what are graphics processing good at? They're very efficient, okay? Each of those cores is very efficient because it does a very similar job. They're designed to allow parallel processing. You know, so obviously you're supposed to use them at the same time. They're very good at mathematics surrounding 3D graphics, matrices, which you can look up if you want to learn more about it. And it works with a CPU to accelerate 3D graphics. Now, a GPU can be used in other areas. So one of them, for example, is some science. You've got some science math can be done using it. Video encoding, they're quite good at. And very modern right now is cryptocurrency mining. GPUs are what are used to do like Bitcoin mining and various others, because the math involved is much better. And also because of the thousands of cores, you can break down the task much better. So anything that can be really parallel processed quite well, a GPU can actually be used for. And that's why it's video encoding, cryptocurrency, and some science and stuff like that. Okay, so, pardon me. So the software, to have a multi-core and parallel system, which we're going on to now just quickly to this bit, but obviously GPU was an example of a multi-core parallel system. The software has, so basically a multi-core parallel system is where all the cores work at the same time. The software has to be written to take advantage of parallel processing. And a very good example is a program such as Cinebench, which I've looked at in another video, which is often used to benchmark multi-core CPUs. Why have I chosen Cinebench again? Well, it visually shows the breakdown of the task as it renders the screen here. And basically, how Cinebench works is it renders a virtual 3D scene. And as you can see, each core would be given a different section of the screen to render. If this was an animation, you could give each core a different frame or something like that. So the software has to be written to enable parallel processing. This is not always possible though, because in some pieces of software, things have to be done sequentially, one after the other, because you're relying on the last task being done for something you need. Games are quite prevalent in this. They can do some use of cores, but they can't tend to use all because things run in a sequence in a game. You have to, if things didn't run in a certain order, it would get buggy. You need to move the enemies, do the shooting, calculate deaths, in order. Maybe you could core some things out, like obviously the radar could be, the sound could be, because if that's 1,000th of a second out, no one's going to notice. And things like that. A web browser is another good example that can be parallel processed because you've got tabs at the top of a web browser. Each tab could be stuck to each core, something similar like that. And the same with video editing software. At the end, when you render out a video, when I do that, I'm recording now and I'll probably do some editing. When you finish, you sort of render the video, you export it out. And multi-core processors are very good at that because it will render out each frame on each core. So yeah, that's basically 1.2 in a nutshell. And there you go.